Hey everybody, Dr. A here, and in this video we're going to be providing some background information on the structural design of square spread footings. And we're going to be referencing the American Concrete Institute ACI 31814 code. And again, this is some background information on how we do this. So before we jump into a lot of the stuff I have written here already, let's go ahead and make sure we know what we're looking at. When we say a square spread footing, what we're talking about is, and I'm gonna draw up here in this top right corner to get us started. When we say a square spread footing, what we're talking about is in plan view, we have a footing like this that has dimensions of maybe B by B. And then in particular, I'm going to be interested in the column being in the middle of the footing with the applied load being a concentric load, okay? Now, again, we can study more about eccentric loading and applied moments and shears, but for this video, I'm going to be looking at the pretty basic, simple case of a square spread footing with a concentric column with a concentric load going right through the center of it with dimensions B by B, okay? So if we were going to look at a side view of this, we would have the column coming down like this, and then we have our footing like this, okay? And that applied load is coming down through the column, and that's gonna engage this bearing pressure here. So you're gonna have this bearing pressure response beneath the footing, and this is gonna be a uniform bearing pressure. We could just call it sigma of some sort, okay? So that's what we're looking at here. If you want to look at a plan view, if you want to look at a plan view and a side view, okay? Now, if you wanted to, maybe sketch a 3D view, you can sketch it out like this. And, you can show the thickness here. And you've got that load coming in right in the center. And, this is B by B, all right? So let's go ahead and get started. How do we size these plan dimensions? How do we get this B by B here? Well, this is going to be based on unfactored loads using the geotechnical allowable bearing capacity. So this step right here is more of a geotechnical step. So if I were to make some little notes here, I would say that the geotechnical capacity, allowable capacity, Q allow, should be equal to the unfactored column force divided by the base area. Now that unfactored column force, that's going to be just adding up, like for example, your dead load and your live load, no LRFD load factors. And that area is going to be B squared, okay? And so you can set all this equal. Now in reality, what you really want, I guess I'll erase this. What I really want is that allowable bearing pressure to be bigger than or equal to that force divided by area here, okay? And so from this, we can rearrange this relationship and we can solve for that base dimension B, okay? So you can do this as a structural engineer or the geotechnical engineer can do this for you. But again, we're talking about unfactored column loads. That's what F represents here. And then we're talking about an allowable bearing capacity, Q allow. Typically, this Q allow already has an ASD factor of safety built into it. For spread footings, most parts of the country in the US, it's usually a factor of safety of 3, sometimes 2.5, sometimes 3.5, but usually 3 is already incorporated into this. And again, this is usually kind of a geotechnical step, okay? Next bullet point here, let's talk about the depth of embedment that is recommended, okay? When we talk about a depth of embedment, what we're talking about is, let's say that we have our column here. I'm gonna draw this little diagram here. And here's our footing, okay? And so when we talk about the depth of embedment, we're talking about, we have the ground surface here, and we're talking about the depth from the ground surface to the bottom of the footing, okay? And we can sometimes call that D sub F. Now, this is also typically recommended in the geotechnical report by the geotechnical engineer working on this. And where this comes from is a combination of things. This depth of embedment that would be recommended in the geotech report will partially be related to this Q allowable, because allowable soil bearing pressure is a function of depth of embedment, but it's also going to account for the frost depth in your area of the country or of the world, okay? Now, what is this thing called frost depth? Well, this is the depth below this ground surface that you could have significant freezing and thawing of the water in the soil, okay? Now, what you want is you want the base of your footing, the base of your foundation, to be at or below the frost depth, okay? So if you're looking at a geotech report and it says somewhere on there, you know, recommend depth of embedment 12 inches or 18 inches or 30 inches because of the frost depth, what that really is accounting for is the potential for water in this soil to freeze and thaw and then displace your footing, or at the very least cause, you know, some potential uplift of the footing here due to freeze and thaw effects, okay? And so if you put the base of your footing below that depth where you could have freezing and thawing of the water in the soil, then you're going to minimize the damage due to the footing and to the whole structure due to that potential uplift, the frost uplift, okay? So so that's, again, this is something that you as a structural engineer, you need to be aware of and be cognizant of. But, you know, the geotechnical engineer or the geotech report will likely give you a recommendation on that. All right, let's talk about this third bullet point. Effective depth of concrete from compression face to centroid of tension steel should be bigger than or equal to 6 inches. Now, if you have your ACI 318.14 in front of you, I'm referencing section 13.3.1.2, okay? And so what does this mean? Well, let's draw a little figure, okay? I'm going to take a look at one part of the footing. All right, let's say that this is like one of these little sides of the footing here, okay? So let's say that we have our rebar here, okay? And let's say we have our rebar also here. So you got that rebar grid there, all right? So what is the effective depth of the concrete compression face to the centroid of the tension steel? Well, remember, for the type of loading we're considering, we're going to have this bearing pressure at the base of the footing, okay? Which means that the bottom region of your footing is what is in tension, which is why you have the rebar down here, okay? Not at the top, all right? And so when we talk about the depth of the compression face to the centroid of the tension steel, we would be talking about from here to the centroid, to the centroid of this rebar right here, okay? And we'll call that little d, all right? So that needs to be bigger than or equal to 6 inches, all right? So you might be thinking, well, what about this other rebar? What about this rebar here that's coming in and out of the screen at us? Well, I mean, that's also going to be a little d value as well, but in the other direction, okay? Because remember, this grid of rebar, you have to have a grid of rebar, and they're not just going to intersect each other. You're going to have one line of rebar on top of the other line of rebar. So the deeper one is what should be bigger than or equal to 6 inches, okay? Now, that's to the centroid. That's to the centroid of that tension steel, all right? So I'm looking at the deeper one of those two, all right? Now, remember, if you look at a D value to the centroid of that upper layer of rebar, you know, it's still going to be close to the D value to the lower level of that rebar, right? There really is just going to be one rebar diameter difference, but nevertheless, measure it to the lower of the layer of rebar to the centroid of that. Now, what about this clear cover to be 3 inches, okay? So I'm going to draw another figure here, but I'm going to zoom in even more, all right? So if I zoom in even more here, okay? And I'm going to look at this rebar here, all right? So, and again, you know, we've got rebar on top here as well, all right? So clear cover is going to be measured from the edge of the concrete where it's touching the soil to the edge of the rebar. That's your clear cover, CC, okay? Not to the centroid of the rebar, but to the edge of the rebar, okay? So you need a full minimum of 3 inches of concrete cover between the edge of your rebar and the edge of that concrete. And that has to be the case all the way around, which means that from the edge of the ends of this rebar to this edge of the footing, that also has to be CC bigger than 3 inches, okay? Now, a lot of times it ends up being 3 inches or 3.5 inches, but it should not be less than 3 inches. The idea is to have plenty of cover of rebar of concrete to protect your rebar from corrosion or other things from the soil that could potentially damage that rebar, okay? And in case you're wanting the reference, that's ACI 31814, table 20.6.1.3.1. Okay, so I encourage you as you're going through this video, have your ACI handy, all right? Let's talk about the limit states, okay? So this is where we get into more of the design calculations. When we talk about limit states, we've got a list of them here that we're gonna need to check. We have the flexural limit state, okay? So, you know, the footing is trying to flex. We have one-way shear. We have two-way shear. We have the development length associated with the flexural reinforcement. And then we have column to footing bearing, all right? So let's talk about each one of these. Let's start with flexure. So in flexure, the ultimate factored moment needs to be less than or equal to phi mn. Now, phi mn, if we remember our basic concrete design, is phi as fy times the quantity D minus A over 2, okay? Now, I'm not going to dig into all of this because I'm assuming that we're somewhat familiar with reinforced concrete design, so I'm not teaching all of reinforced concrete design from scratch in this video. But we like to say D minus A over 2 is approximately equal to JD, okay? Now, what is D? Well, D is that same depth we talked about earlier, the depth from the compression face to the centroid of some steel. And we're going to assume J is 0.9, okay? You can also assume it's 0.85, 0.95, but generally I just assume it's 0.9. We're also going to get the ball rolling by assuming that we have a tension-controlled section, and so that'll let us assume phi is 0.9, and we can reference table 21.2.1 in ACI for that. And so when we incorporate this in, we're going to have MU. Here's that MU, must be less than or equal to 0.9 ASFYJD. And this J is also 0.9, so we have two different 0.9s here. And so we can do some rearranging, and we can say, okay, we need some steel A sub S that is bigger than or equal to MU divided by 0.9 FY times 0.9 of D, okay? And so from there, we can get an estimate of how much rebar we need in a particular direction. So this AS is going to be the rebar in one particular direction. It is not incorporating or accounting for the rebar in the other direction, okay? So that's in one direction. Now, the rebar in the other direction should probably end up being about the same, right, if we're dealing with a square footing with concentric loading, all right? So let's talk about MU. This is what people kind of get tripped up on a lot, all right? When we talk about MU, here's what we're dealing with, all right? We're going to have this column here, okay, and we're going to have a force coming in here. I'm going to call this F sub U, all right, or you could call it maybe P sub U, All right, now this is going to be a factored column force, okay? This is your LRFD factored column force. And so here you're going to get this bearing pressure, all right? And if everything is concentric and centered, you're going to get a sigma sub u. Again, this has your LRFD load factors in there. So for example, 1.2 dead plus 1.6 live, all right? And what you're doing here is you are looking at MU at a critical section, okay? So where is this MU occurring in this nice little figure that I drew here? Well, it depends on what the column is made out of, all right? So if we have a concrete column, MU is going to be at the face of the column right here, okay? So we're going to be looking at MU right here. There's MU, and this right here is called the critical section for MU. All right, and so what do we do here? What we're going to do is we're going to use method of sections, if you remember that from statics, and we're going to make a cut section at that critical section. Okay, so this cut section is right here at the face of the column. All right, and then what we're going to do is we're going to look at a free body diagram of this. Okay, and here's sigma sub u, all right? And what we're going to end up looking at is, okay, what is this MU value right here at this cut section, all right? What is MU? And so from here, what we can do is say sum of the moments about the cut equals 0. Basically what we're doing is it's just an equilibrium equation, okay? Now the question becomes, how do we calculate this MU here, okay? Well, again, you should have some dimensions here, all right? We know that this entire base is B, okay? And then we're going to call the width of this column, we're going to call this little c, and I'm just going to call it little c because that's what ACI calls it, all right? So then what is this dimension here? Well, if we just do some basic measurements, this is going to be B over 2 minus C over 2, okay? Or you could repackage this as just B minus C over 2, least common denominator, okay? How do I know that? Well, again, this whole thing is B, and so if I say B over 2, that takes me to the center line of the column, and then I subtract C over 2 to get me to the face of the column, okay? And so if I do that, I can end up basically saying, hey, MU is going to be equal to sigma sub u times B minus C over 2 times what? Well, I'm going to say times B minus C over 2 divided by 2, and then times another B out here, okay? Now, how did I come up with this? Well, clearly what I've been able to do is I've been able to say, okay, the centroid of sigma u is right here in the middle of the B minus C over 2 dimension, okay? Right there in the middle, okay? And so I say sigma u times B minus C over 2. That gets me this equivalent load right in the middle. And then I say another times B minus C over 2 divided by 2. That gives me this dimension right here. Now, what about this other B that I threw out here? Well, this other B is the other B dimension. Because remember, this is a square footing. So this is the B that's coming out of the screen at you, all right? So in total, this MU can be written as sigma u times B over 2 times B minus C over 2 squared, okay? So you can repackage this as this handy little formula, or just use basic statics like I just did, okay? So now that's if your critical moment section is at the face of the column, which is the case if you have a concrete column. Now, what if you have a steel column, or you have a masonry column or a masonry wall? Where is that critical section? Well, I'm going to put a note here. I'm going to say C10 table 13.2.7.1 because that has other critical sections where MU is located. If you have a different kind of column or a different kind of wall, let's say you have a column on a steel base plate, or let's say you have a masonry column or wall. Well, the critical section is not always going to be at that face right there. It could be at a slightly different location. So take a look at that table in ACI to help you find where the other critical sections are. When you do that, the MU value you're going to calculate is going to be a little bit different because these dimensions will be a little bit different. All right. Let's talk about one-way shear. Okay. One-way shear is very much the same as beam shear. All right. So what I'm calling VU1, that's one-way shear. It must be less than or equal to phi VC1. Okay. Now that is equal to phi 2 times lambda times the square root of f prime c times b times d. All right, a lot of similar variables here that we've seen before and that we're familiar with, hopefully, with beams. Okay, phi is 0.75. That's the LRFD resistance factor. You can find that table 21.2.1. All right, now where is this VU1 here? Okay, VU1 is, let's go ahead and draw this again. All right, I'm going to draw my column again with the footing. All right, and there's that factored column load, F sub U, all right, or P sub U, whatever you want to call it. And, you know, here is our bearing pressure. Same diagram as before, same diagram as we saw up here, all right? Now, here, your critical one-way shear plane or one-way shear section is going to be right here, okay? And so what you are going to have here is this VU1. Now, this critical plane is going to be a distance of D away from the column. So similar to what we did in that previous step, I'm going to use method of sections, all right? And I've got, you know, this bearing pressure here. There's that sigma U, just like in the previous illustration, except what is this dimension line going to be now? It's not the same dimension line that we saw for the critical moment section, okay? So again, if this is you know, B and this is, you know, C right here. So how do I get this dimension here? Well, similar to what I did before, I just measure things out, but I also subtract out a D value, okay? So what I'm looking for is this length right here, okay? This length, this horizontal length. So I'm going to say B over 2, right, minus C over 2 minus D, all right? Or you could, you know, repackage that as B minus C over 2 minus D, okay? And that's what this dimension line is here. And so if I'm looking for the shear force here, okay, VU1, how do I get that? Well, it really just comes from sum of the forces in the y direction equals 0, all right? And so by doing a little bit of rearranging, I can end up getting what? VU1 equals sigma U times, make a bracket here, times B minus C over 2 minus D times B, okay? And so what have I done here? I've said, okay, sigma U, that's this uniform pressure, times this dimension line, that's the B minus C over 2 minus D, times this B right here. This B is the B that's coming out of the screen at you. It's the other dimension because this is a square footing, all right? All right, let's look at the next limit state, two-way shear. We sometimes call two-way shear punching shear, okay? Now, for punching shear, we say VU2 must be less than or equal to phi VC2. Phi is still 0.75 like it was before. Now, VC2 is going to be the minimum of these three terms, either 4 or 2 plus 4 over beta, or 2 plus alpha S d over B naught, all times lambda F prime C, okay? By the way, in case you don't remember from concrete theory, lambda is a modification factor if you have lightweight concrete or normal weight concrete. Lambda is 1 if you have normal weight concrete, okay? And that's the same lambda we saw up here for one-way shear, by the way. So you can find this in table 22652 of ACI 318.14, okay? So let's talk about this VU2, okay? Punching shear. What is that? Well, with punching shear, what we have here is we have our square spread footing, all right? And we have this column here, all right? And so what's happening is this column is going to tend to want to punch through the footing, okay? So you could have this scenario, especially if the footing is very thin compared to the column dimensions. If you have like a very large cross-section column but a thin footing, you could have that column that will tend to want to punch through the footing, okay? And so how is it going to want to punch through the footing? Well, it's going to want to punch through this larger area that is surrounding the column, okay? We call this this perimeter the punching shear perimeter, okay? Now, what are these two dimensions? All right, well, the punching shear perimeter is going to be defined based on moving a distance d over 2 out in the two principal directions from the column, okay? So if I move d over 2 out away from the column along all four sides, then I'm going to get these dimension lines as C plus D, okay? And so this B naught value is what we call the punching shear perimeter, all right? And what is that going to be equal to? Well, it's going to be equal to 4 times C plus D, okay? Because you have 1, 2, 3, 4. And again, we're assuming we have a square column, by the way. You know, C is the cross-section dimension of the column, and if it's a square column, then the column is C by C, okay? Now, what about these other values that are kind of in the mix here? If we have beta and alpha sub S. So beta is the ratio of the short side to the long side of the column. You can find that. I'm actually opening up my ACI right now so I can tell you the correct page, or the correct reference. If you're looking at around table 22.6.5.2 in ACI, if you look on the right column, it says ratio beta of the lengths of the long and short sides of the column, okay? So beta would be equal to 1 for a square column, okay? Now, what about alpha sub S, okay? Alpha sub S is given in 22.653 of ACI. That's on the very next page. And alpha sub S is 40 for interior columns, 30 for edge columns, and 20 for corner columns. So alpha sub S will be 40 for interior footing columns. So basically what this accounts for is for a footing, if the column is in the center of the footing, you use alpha S as 40. If you had a column at the edge of a footing, you would use it as 30, and if you had a column at the corner, it would be 20. So one way you can remember that is alpha sub S is 10 times the number of sides that the column will punch through of the footing, okay? So if you got a center located column, that column will tend to punch through 4 different edges here. So that's 4 times 10 is 40. Now, two-way shear, we also see it in slabs a lot too, like elevated slabs, roof slabs, floor slabs, or whatever. And so that's where, you could come across when you have a slab situation, you could end up having A sub S is 20 or 30. But for concentrically loaded footings, most of the time alpha S is going to be 40, okay? Now, the question becomes, how do we calculate V sub U? I'm going to do that in another video, but this is kind of the background on VC, okay? So don't worry, I have not forgotten about how do we get VU too. We're going to see that in another video, okay? Development length, okay? Just like in beams, we got to worry about development length being less than the available length, okay? So the L available is measured from the critical flexure plane, okay? Table 25.4.2.2 may be used to get you LD. So what do we mean by critical flexure plane? Again, if you have your side of the footing right here, okay, and we're going to call this right here the critical section or the critical plane for MU, okay, then you're going to have your rebar running here, okay, and so the available length is going to be measured from that plane out to here, okay. Now, what typically L available is going to be is something like this. L available is going to be B minus C over 2 minus the clear cover, okay? And you remember this clear cover is how much? It's 3 inches for concrete cast permanently against soil, okay? So it's the width of the footing minus the width of the column divided by 2, all right, minus that clear cover, all right? So that's your L available when you have concrete columns. Now remember that critical plane for MU might be different. It might not be at the face of the column if you have a steel column or you have a steel base plate or you have a masonry wall or column. So keep that in mind, okay? Let's talk about the last important limit state that we need to be aware of, and this is the column to footing bearing, okay? So what do we mean by that? Well, let's say that we have a column here, all right, and we have the footing here. So this column is bearing on the footing, okay? This column is bearing on the footing. Now, you might have a base plate here, or it might be, you pour the column here and you have some kind of, little key here. But regardless, this column is going to be bearing on the surface of the footing, all right? And so what you have to ensure is that the factored load, which, in this video I've been calling it FU, is going to be transferred from the column through this interface into the footing, okay? And so what you have to ensure is that BU is less than or equal to phi BN, all right? Now that FU from the column, the factored column force, is BU, all right? That is BU. Phi is going to be equal to 0.65 because why? Well, 0.65 is our LRFD resistance factor related to compression controlled. And, in this case, columns, most of the time when you're dealing with bearing between the column and a footing, you got a compression controlled scenario. So BN is going to be the minimum of square root of A2 over A1 times 0.85. It's the smaller of that and 2 times 0.85, all multiplied by F prime C times A1, okay? Now the question is, what's A1 and what's A2, right? So A1 is the bearing area, that's the interface between the column and the footing, A1. If you have a square column, that's just going to be C squared, okay? That's just going to be C squared. What about A2, okay? What about A2? Well, A2 is a projected area down into the footing, okay? And then it's this base area down here, A2, okay? So what is that? How do we get that? Well, A2 is going to be obtained by projecting a one vertical to two horizontal area down to the base of the footing. Okay, so A2 should still be square. It should be some kind of square area, but it comes from a 2-to-1 ratio. So, for example, let's say that you have a thickness of capital T here of your footing, okay? So if that's capital T thickness, then what is this dimension going to be here? What is this dimension going to be here? Well, you go down by T, and so you're going to move over by what? By 2T. Okay, 2T. And so what is this middle dimension here? That's your width of your column C. So this is going to be 4T plus C. So that means your A2, this A2 right here, is going to be 4T plus C squared if you have a square column. Okay, so that's the conclusion of this video. I know it's kind of a lot of background information. This is not meant to be a numerical example. We're going to have that in another video. And in that other video, we're going to also, see numerical examples of all of these limit states kind of put all together for a full design example. But this is meant to just give you some background information on what you're looking for and what you need to be checking when you have square spread footings with concentric column loads and you've got a square column cross section. So hopefully you found this video helpful. If you did, please hit like and subscribe, and be on the lookout for the other spread footing video or videos that I'll be posting that go with this background information.